One of the reasons we can, that Newton and Leibniz were able to kind of develop shortcuts for the limit definition is because there are certain patterns that will occur for certain types of functions. Polynomial functions will follow a certain pattern of behaviors. Log functions follow a certain pattern of behaviors. Trig functions follow a certain pattern of behaviors. One of the patterns of behaviors for when we're doing this with a polynomial is when you get to this point, your constants should add out to 0. If your constants don't completely add out to 0, you've made some kind of arithmetic mistake. 1 minus 2 is -1, plus 3 is -2, or is 2, excuse me, minus 2 is 0. These four constants, or however many constants you have, they should add to 0. If they don't add to 0, that's a red flag. Okay. Let's see. Does this give you... No, wait, okay, what did I do wrong? Crap, what did I do wrong? Something's wrong. Maybe not. Hang on. Oh, it is going to be. Oh, crap. Okay, I didn't mean for this one to come out this way, but it is. Okay. So, here we go. It is right. Okay. These guys may or may not add out to 0. Okay, it happens to be in this case that they do. So when you're left in this situation, I should have picked a better problem. I'm only left with h squared over h. Sometimes I'll be left with something like h squared plus 5h or h squared minus 10h. We're doing a quadratic, another quadratic this time. Quadratics will act a certain way. Cubes will act a certain way. Lots of patterns. This is still 0 over 0 unless I take out an h. Yeah, I hate that this came out to be 0, but it is what it is. It is 0. That is right. I shortcut checked it, and it is 0. Let me think about that for a second. Yeah, is it really? 2, yeah, -2, crap. Okay, just a dumb answer. Okay, that's all right. It's more about the process at this point. And I'm actually kind of glad that this one sort of worked a little differently. Pretty much the only thing you can definitely count on is the constants adding out to 0. Okay, how'd we do? I mean, it's a little weird. This one was a little weird because of how it came out. Ian, question, you're okay? All right. Now, there is another form for the limit definition of the derivative. This one is more about, instead of taking one point and moving it close to the other so that delta x becomes a 0, it's more about taking the 2 points and moving them close together. So anyway, it's another version of y2 minus y1 over x2 minus x1. It's just as x approaches a. So let me show you how this will work. You might like this form better. It doesn't matter to me if I say I need you to use the limit form of the derivative to find the derivative value. It's fine to do either one. You will be expected to recognize both forms. So you will need this form memorized as well. Okay. So let's look at how this is going to work. A slightly different limit setup. This time we're going to do f of x and f of a over x minus a. So if we're doing f prime at 3, that means a is 3. So I'm going to do the limit as x approaches 3 of the f of x function, exactly the way it looks, minus the f of x function with a substituted in, so f of a. Okay. So this is f of x, and this is f of 3 over x minus 3. I tend to prefer this version of the limit definition of the derivative. The algebra seems to work more nicely for me in this case. I always preferred this version. You may feel that same way. Just kind of depends on your perspective. Why is this not being my friend? There we go. Close that down. Close that down. Okay, and so this is going to be x minus 3. Okay. Now, this happens to be a root, which is going to take us down a slightly different path. And we could absolutely do this problem using the other definition. It tends to be a little messier, but it'll work. But just like the first definition, when we go to apply the limit definition to a function to find that function's derivative value, invariably the limit is a 0 over 0. So, from our last unit, from our chapter test last week, how do we calculate a limit like this when we're running into the 0 over 0? Good. And what's that called? The radical x minus 2 plus 1? Called the conjugate, right. X minus 2 minus 1, x minus 3, root x minus 2 plus 1, x minus 2 plus 1. Bam, 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 bam. Okay. Now, this problem came out to be a conjugate problem not because I used a different form of the limit definition, it's because it was a root. I just want to make sure we're clear. I changed formulas on you, but I also changed the type of function you're working with. Whatever type of f of x you're working with, the limit is going to present a little differently, and you will have different challenges for calculating the limit regardless of which definition you use. All right, so let's see if you guys remember how to do this. All right, non-conjugates, let them sit next to each other, just hang out. Multiply your conjugates. Root x minus 2 times root x minus 2 gives me x minus 2. When I multiply conjugates, the O and the I, the outside and the inside of the FOIL, add out to 0. A squared minus b squared is the result when I multiply a minus b and a plus b, two conjugates. So this is the limit as x approaches 3 of x minus 3 over x minus 3 times x minus 2 plus 1. Final answer? Well, I take out the common factor that's making the 0 over 0. Final answer? 1/2. 1 over the square root of 3 minus 2. If we were using the H formula, we would still have to use a conjugate. It would just be a little messier in terms of the algebra. Like I said, I tend to really like this alternate form. You are going to have to be able to recognize both forms. Now, how does this get tested on the AP exam, which is always like kind of a valid question. Oftentimes, what they'll do is they'll give you a limit problem to do that is actually a derivative. And if you know that it's a limit that's in fact a derivative, you can do it a shortcut way versus trying to do the big limit, all of this stuff. So that's usually what they test you on. They don't always test you on expanding and calculating the value, because most of the time you know the shortcuts. I don't know that I've ever seen a free response where they've asked you to expand out the limit definition of the derivative. That doesn't mean I'm not going to make you do it, because I am. But most of the time where I have seen this problem, it is more about, if you see a limit like this, if you recognize it's a derivative, then you can actually do the problem a quicker way. If you don't recognize it, then you can still solve the problem, but it takes you a lot longer to do, therefore eating up a bunch of time, which is an issue when you're taking the timed exam. Now, homework problems you're going to do, you're going to practice this. In your book, it's going to give you a function, it's going to give you an a value, it has a couple problems, it's going to say use this definition, and then it's going to give you a couple problems that say use this definition. I recommend practicing both. Okay. No reason not to. Okay, last part. Instantaneous rate of change, derivative. Also called the slope of the tangent line. If I can calculate f prime of a is the slope of the tangent line to f of x at x equals a. It's the derivative of f at a. It's the value of the derivative of f at a. It's the instantaneous rate of change of f at a. It's the slope of the tangent line to f of x at x equals a. There's lots and lots and lots of different synonyms, code words for derivatives. Derivatives, tangent line slopes, instantaneous rates of change. Tangent lines happen to be super helpful for solving lots of different kinds of problems. Lots of very, very complicated function models can be linearized, meaning you can use a line, a linear function, to approximate small sections of it. So being able to talk about some curvy, crazy section of a function and model it with a line is a huge tool of calculus. The tangent line is the magic line we're going to be interested in coming up with. And so problems where we're being asked to write the equation of the tangent line are going to happen over and over and over and over again. So, slope of the tangent line, equation of the tangent line, you're going to do that over and over and over again with different kinds of functions I will be asking you to do this in October, November, December, January, February, March, April, and May, up to whatever the test is, May 9th, I think, or 8th, something like that. Slope of the tangent line, equation of the tangent line. Learn it, live it, love it. So let's do one. Find the slope of the tangent line to this function at x equals 2. So what does that mean? That means I need the derivative of 1 over x at x equals 2. Which definition do you want to use to find my derivative? You want to use the first one or the second one? Second one? Okay. So the second one is the limit as x approaches 2 of my f of x function minus f of 2 all divided by x minus 2, right? F of x minus f of a over x minus a. What happens when we try to find that limit? What do we get? We get 0 over 0. Okay. So what magic trick MacGyver thing are we going to pull out of our toolbox to deal with this guy? How about a common denominator for these fractions? Yes. Let's multiply that one by x and that one by 2. So both a form of 1. So we're going to have the limit as x approaches 2 of 2 over 2x minus x over 2x all divided by x minus 2. So if I put those two fractions together, it's 2 minus x all divided by 2x, and then all divided by x minus 2. We don't like complex fractions like that. Nobody likes those. But luckily, I got algebra skills that help me. So I can do the limit as x approaches 2 of 2 minus x over 2x times 1 over x minus 2. Dividing by x minus 2 is the same as multiplying by the reciprocal of that, which is 1 over x minus 2. Now when I get to that limit, remember, all of these algebra tricks ultimately lead to me hopefully being able to divide something away. X minus 2 and 2 minus x leave me a negative 1. My value is negative 1/4. Now, before you get to kind of like, oh, cool, we're almost done. That's only half of the problem. That is the slope. Okay, so what I just figured out is that the slope of the tangent line to 1 over x at x equals 2 equals negative 1/4. Now we're going to write that tangent line equation. And to do that, we're going to go back to an old friend from Algebra 1, Mr. Point Slope form. Oh no, no, we're going to love point slope. Mr. Point Slope form looks like this. Y minus y1 equals m times x minus x1. It's actually going to be our favorite way to write the equation of a line. It's the easiest one to do in a calculus setting, because most of the time in a calculus setting, the things I'm going to get are enough information to create a point and the slope, hence point slope form. So, the negative 1/4, where does that go? That's m. X and Y are X and Y. They don't change. X1 and Y1 is a specific point on the function. Now, they told us the X value of the point. They told us they want to go to X equals 2. So that means X1 is 2. What's Y1? Thank you. Where did you get that? Yeah, that's the function. Anytime we want the equation of a line, I'm going to say, what do we need? And you're going to say, we need a point and a slope. And then I'm going to ask you where we're going to get those things. The slope is the derivative. The slope of the tangent line is the derivative. The point on the tangent line, there might be different things we have to do to get all the information about the point. We might be given the point to write the tangent line at. We might just be given the x value, a lot of times just the x value, but we've got the function so we can create the y. And so there is my tangent line equation. No. I actually would prefer, and I will encourage you to not convert it. And here is why. The more times you write things down, the more likely you are to write something down incorrectly. So every minute you spend fiddling with that equation, A, it's wasted time, and 2, you're likely to make a mistake. So I would 100% stop right there. It's an equation of a line. It's good to go. It does not have to be in y equals mx plus b. That is not a better form. It's a better form if we're going to graph it, but we're not graphing this. We're just writing it. So stop yourself at point slope form. One more thing to show you, one more thing to tell you about your homework. I know this is going to take you out of process. You have a couple questions to do at the end of the homework to practice tangent lines, and we're going to continue to practice this. The two things I wanted to tell you, though, are in your homework, you're going to be asked to also write the equation of a normal line. I don't know if this comes up anywhere else. Have you ever heard of that before? Okay. So here would be the normal line. To that tangent line. How are they related? They're perpendicular. How do you know that they're perpendicular? Their slopes are opposite reciprocals. Yes, that is the definition of the normal line. The normal line is perpendicular to the tangent line. So if you make a tangent line, you can make a normal line. in 2 seconds. We'll pick up with the very last problem next time. It's not a big deal. It's kind of just an add-on, and we can throw on there. Lots to digest today. You cannot go forward from this without thinking and practicing. Okay?